Thank you, Ruben, for having me back. It's an honor to be invited back. It's always a joy to come to Spain and Madrid, so I definitely appreciate the chance to come back and talk to you guys again. Let me tell you just a little bit about myself, kind of my background, how I got started in this, and then I want to talk today about a lot of what's going on in Hadoop and Hive, particularly around faster interactive query and expanding the SQL in Hive. So I actually got started with Hadoop projects in the summer of 2007, which kind of is ancient history in the Hadoop world. I was actually thinking it was really funny. In 2009, I went to VLDB to present on Pig, which we had just written. That was what I first got involved with. And when I came there, I was the brand new guy advocating this crazy new thing called Hadoop, and all the database people were looking at me like I was some wild-eyed crazy youth, right? And now I come here 4 years later, and I'm the guy selling the old, Hadoop, while there's this all these brand new things being talked about. So in software, you age out pretty early, 4 years, and I've gone from the crazy-eyed youth to the old guy. Anyway, so I started out working on Pig and Yahoo. That was developed in Yahoo Research when they decided to make it a product that their engineers and analysts could use. That I joined the team to help make it a production-ready product, kept working on that, transitioned into working on the metadata and HCatalog, and now I still work on both those things, and I also work on Hive. As Ruben mentioned, I'm one of the co-founders of Hortonworks, which has been a great thing. It's been a lot of fun to work on that and to see Hadoop really go from something used by a few web properties to a mainstream product used now around the world by all kinds of different industries. All right, so what am I here to talk about today? We've heard lots of stuff about how batch is kind of the old thing, how there's all this focus now on new, interactive, real-time type processing in Hadoop. Let me first say that I still think actually batch is very important. There's a whole set of things that the batch is important for, but the focus on interactive and real-time is important, and so I want to talk to you today about kind of some of the changes happening in Hadoop and specifically in Hive to enable that. So let me start with just a little background on Hadoop 2 and some of the changes in that. And we talked a little bit about this yesterday in the panel, because one of the questions was what's new in Hadoop 2. And I talked then about Yarn and how that enables new processing models on Hadoop. And this is really, really important. It's key, really, to taking Hadoop from something that does MapReduce well, very well, to something that can truly be a giant parallel processing engine, right? So as we talked about, Yarn opens up the processing model to all these different types of applications. So what Yarn does is separates out the execution engine, which is MapReduce, from the resource planning. So in the past, in MapReduce or in Hadoop 1, when all you had is MapReduce, both resource planning and execution was handled in the MapReduce layer by an element called the job tracker. It did both. By splitting the job tracker in half, creating what Yarn now calls the resource manager, which is in charge only of allocating resources inside the cluster, and making the rest of the job tracker, now called an application manager, application master, an app master, by making that individual to the type of job you're doing instead of there being one for the whole cluster, we can now have all these different kinds of applications. So you still see batch with MapReduce over here. You see interactive relational type stuff with Tez, which I'll be talking about. You can do HBase now integrated into your cluster instead of running it on the side. You can open up models like Storm, in-memory processing like Spark, graph processing in Giraffe, all kinds of other things. And we see all these things moving into Hadoop with Yarn. So this is crucial for really opening up Hadoop to all these other processing models. So the one of these that I want to focus on today because it's important to Hive is a new application called Tez that we're developing or helping develop inside Hortonworks, along with others in the Apache community. So what is Tez? What's the point of this? So it's actually the Hindi word for speed or quickness. And the focus here is that, as you've heard over and over in this conference, MapReduce is great at certain things, but it's not what you would design. It's not what you would build if you wanted to build a relational system on top of a parallel processing engine. It's just not what you'd set out to design. MapReduce is really good at group by, it's pretty good at sort, but once you get to join, it's actually not a good solution. And it's also not good because it was built around the assumption that jobs are going to take hours. And so if it takes 30 seconds to start up a MapReduce job, who cares? That's noise, right? I mean, basically you can think of it as MapReduce is a freight train. And if you need to move, 50,000 tons of steel from your steel factory to your automobile factory, the fact that the train takes a while to get moving and may not go that fast, that's all fine because you can't exactly load 50,000 tons of steel in your car. But when you want to do something fast, when you have a human sitting at the end of the terminal asking queries, suddenly those priorities shift, right? And so that's where we want to take Tez. We want to make it so that it is the engine you would want to build these, to build a SQL layer on top of, or even other types of relational processing. It's actually kind of amusing. Within 6 months of starting with the team at Yahoo and working on Pig, I remember going to Owen O'Malley and Arun Murthy, who are the leads for MapReduce, and we're working on it from close to day one, and saying to them, MapReduce isn't really what I want to build Pig on. I want to change it this way and that way and the other way. And they're like, no, you don't. MapReduce is great. I'm like, yes, I do. I want to change it. I want to change these things. And over time and talking with them, and eventually convincing them that, yeah, MapReduce isn't exactly what I want. That this is, these kind of conversations between us over the years and input from others and seeing things is where these kinds of ideas come from. So it's something we've known we wanted for a long time, but we needed Yarn to make it possible. Without Yarn, you couldn't actually do this stuff. So, okay, so how does Tez work? What's the idea? A good way to think about this is just to compare it directly to how MapReduce works, because everybody understands that, right? So up here on the left, you have a map in a MapReduce task. So what's a map do? It takes input from HDFS, applies some processing, and it produces sorted output. That is a map task. And a classic reduce task takes that sorted, shuffled input, does some processing, writes to HDFS. That's all MapReduce does. It's part of the beauty of it. It's very simple. But one of the observations of Tez is, what if you could take this and mix and match? What if you could produce this down here, which is a reducer that takes shuffled input like a reducer, does some processing, but then it produces sorted output like a map? What if this could be an intermediate reduce step so that you could go map to reduce and keep reducing instead of do another map? So you can think of at least one of the first steps in the Tez project is to take MapReduce and generalize it, to generalize it into something that can process arbitrary DAGs of operators instead of something that always has to do a map and reduce. So let's look at how that might play out in a real Hive query. So up top here we have a simple Hive or a simple SQL query, which is admittedly a little bit fabricated because I needed something to produce this kind of plan over here. But it's a select with a join, and then you're going to union that with a select with a group by. So on the left here, you see the MapReduce plan that Hive 1 would produce for this type of query. So there's a MapReduce job. Whoop. There we go. There's a MapReduce job here to do the first join. There's another one to do the group by. There's one to do the lower group by over here, and then you end up doing the union together here, right? So you need, a total of 4 MapReduce jobs to execute this query. And there's a bunch of writes to HDFS in here in between, right? So there's lots and lots of issues with this query that, or sorry, with this execution of this query that's non-optimal, right? If you look, let's just look at a few of those. One of them here are these writes to HDFS. HDFS is great as a distributed file system, very reliable, performs well in parallel, all that kind of stuff, but it wasn't built as a way to transfer data in between jobs at high speed. Now, if you think these jobs are going to take an hour each, writing to HDFS actually makes a lot of sense because you want to persist the results in the case of failure. You want to be able to back up to the previous job and go again. But if you think that each of these jobs is going to take 5 seconds, taking the time to write to HDFS in between is actually really painful and is going to slow your query rate down and really doesn't matter because if you estimate the entire query is going to finish in under 30 seconds, who cares if you blow up at the end and it doesn't work, you just rerun the entire thing, right? There's no need to persist the intermediate results. Another issue here is these map tasks, the lower green map tasks after the initial one, so these 4 here, are totally useless. Anything you can do in those, you can always push into the preceding reduces. So you're doing extra processing just because that's what your model demands. There's no ability in MapReduce to say, I just want to reduce. You always have to map first. And then you also have issues that, these kind of multiple input type queries like here, or multiple input type jobs, that's not actually very natural in MapReduce. You have to kind of play some strange games in your code to make that happen. And actually a surprising amount of code in Pig and Hive is just doing what I call black magic, tricking MapReduce into thinking it's doing one thing when it's really doing something else. On the right here is what this looks like if you do it in Tez. So you notice this is a general DAG. We've got operators like this that are taking input from multiple sides. You've got reduce followed by reduce here. There's no writes to HDFS in between. And in fact, the goal here with Tez is that how you move this data between these tasks is chosen by the optimizer of the application, like Pig or Hive, based on its expectations of the query. So again, if you expect these jobs to take a long time, then you're gonna choose to persist that to local disks, maybe even to HDFS, depending on the trade-offs you want to make between performance and reliability. But if you expect that this whole thing is going to go very fast, you might choose to move these, to stream this through a socket. Or if your scheduler happens to realize, hey, these 2 tasks are actually running on the same machine, you might even move it in memory. You might just, mmap a file and share it between them or something. All those are options in a Tez world where it's making choices, or where it's building that whole graph and it understands it. The other thing that's important here is, in this old world, over here in MapReduce, the job tracker had no understanding that those 4 jobs were related. Hive or Pig or whatever's running this query had to understand that on top, and it had to submit them in the order that, in a dependency order, but it couldn't give them to the job tracker all at once and have it track them all together. So you might run your first 2 jobs, and then on a busy cluster, you might wait 15 minutes for your next job to finish, to even get started. So you're burning time waiting because the scheduler couldn't understand they were all related and needed to schedule them together. In this world, it's all one job. Tez understands the complete, how your job fits together, and it can work with Yarn to schedule that job in a way that's efficient so that it doesn't end up starting the query and then taking a long pause and that kind of stuff. All right, so there's one other issue that still remains that what I've showed you so far doesn't address, which is MapReduce, Hadoop in general, tends to have long startup times. I mean, as you know, when you write a MapReduce job, what happens? It picks up your jar, it ships it to all the machines it's going to run it on, it starts new JVMs on those machines, and then finally your query can run. So you're paying, depending on the size of your cluster and busyness and all that, a 15 to 30 second overhead before your job even starts, right? That's just getting the jars distributed out there, getting JVM spun up, all that kind of stuff. And again, in the batch world where your thing's going to run for 2 hours, hey, that's fine. In an interactive world, that's not so great. So what are we doing about that? Another thing that Tez supports here is sessions for users. So when you, as, for example, a Hive user, connect to the system, it can start up a session, it can pre-spawn containers to run these operations, so that when you input your query, it can actually run that, it can run almost instantly. I mean, obviously there's still a little bit of planning time for the query and all that, but that we can push down in the 500 millisecond or 1 second range where we're doing the planning, but we can actually be processing data very, very quickly once that session is up and running. So this is another important element in enabling these kinds of interactive operations in the Hive world. So this is kind of a summary slide of all that stuff I've talked about. So I'm not going to go back over that. But that's kind of lays the groundwork for making that possible. All right, so now let's move a little bit more to Hive itself. The goal of Tez is to enable these things, not just for Hive, but also for Pig. There's actually already a project going on between Hortonworks, Yahoo, LinkedIn, and Netflix to also port Pig to work on Tez. We envision other frameworks like cascading moving to it. We've talked to the concurrent guys, and they're on board with eventually moving cascading into Tez as well. So that's the groundwork. But now, how do we want to move that forward in Hive? So last year, we published a blog saying that we would make Hive 100 times faster, and that we would move Hive SQL into what people want it to be. Actually, a small amusing anecdote about the 100 times faster. I actually wrote that blog post, and nowhere in the blog post did I say the words 100 times faster. I just said it was going to be a lot faster. And then when the marketing guys who actually posted the blog put it up, they put that in the title. But I had no idea. So I come into work, and the first thing my manager says to me is, "What in the world do you mean we're going to be 100 times faster? Why did you say that?" I'm like, "What are you talking about? I didn't say that." So the lesson is, don't just write your blog post. Actually make sure you title it, and don't let the marketing guys title it for you. But all that said, we did say we wanted to make, once your name's on it, you own it, whether you wrote the title or not. So we said we wanted to make Hive 100 times faster. But that's not the only thing we wanted to do, right? There are two other goals. One is Hive is good at scale. That's where it grew up. That's the world it came from. That is, its original use case really was ETL for Facebook. We don't want to break that. One of the things that we see happening in the Hadoop world that we actually think is pretty bad is kind of this bifurcation of, okay, big batch type things, you go over here, you use these tools. Fast interactive things, you go over there, you use those tools. We don't think that's actually going to work very well in the SQL world. Now, there's times that's appropriate, don't get me wrong. I'm not saying MapReduce should solve every problem or you should move all your MapReduce programming to Storm. Storm is great for certain sets of things, MapReduce is great for certain sets of things, but I don't think you want to have separate SQL engines doing separate things, because what's going to happen in that world? What's going to happen is you're going to build dialects of SQL, and you're going to have users that need to go across both. And they're not going to be able to remember, okay, I want to use this tool when it's big, but this tool when it's small, and this one supports this flavor of SQL, but this one doesn't, or my user-defined function that I wrote works over here, but it doesn't work over there, or vice versa. You don't want that, right? You want one SQL front end that all your user base can use, and that SQL front end underneath figures out, okay, I need to plan this in a batch way, or I need to plan this in an interactive way, depending on what I'm trying to do. Right? So we want to keep that batch still working. We want it to scale well. The next point is people, as I said, Hive grew up basically as an ETL engine, so its SQL tended to do the things well that you needed in ETL. It did big joins, it did group bys, it did, that's really pretty much what it focused on, group by and join, because that's what you needed in that world. And the adoption curve we see in Hadoop, and I think in other big data projects, tend to be the first people to it are the engineers, right? And the first use cases they tended to bring in the Hadoop world were ETL. But as Hadoop gets more mainstream, the next generation of people who are being exposed to it are analysts. They're people who don't do Java programming. They don't want to write a user-defined function to do everything they need to do. And they come from a SQL that's much richer than what Hive has, right? Hive's SQL was initially was pretty primitive. These people are coming from Oracle, from Postgres, from Teradata, where there's much richer versions of SQL. So one of the things that we said is we want to take Hive SQL and we want to move it forward into what these users expect. This doesn't mean we want to make it, people ask me all the time, when is Hive going to be SQL 92 compliant? When is it going to be SQL 2003 compliant? We actually don't spend time worrying about whether it meets every part of the SQL 92 spec. I don't actually think that's important. What I do think is important is that it meets the spec in the things that it does. So when it adds a new functionality, it does it in line with the way, with the standard. But what's more important is that it does the things people want. So we're handpicking parts from different specs. For example, in Hive 11, windowing functions were added in the over clause. That's from SQL 2003. Why did we do that? Because that's something we believe is important. And users were asking for. They're saying, hey, this is stuff we want to do. Right now we're going through crazy contortions to make Hive do these kinds of things. So we went and added that. So now you can do rank, row number, first, last, lead, lag, all those kinds of things. So that's this last point here. We want analysts to be able to use it. We want your BI tools to be able to use it, right? When you bring Tableau, MicroStrategies, whatever BI tools you use in your stack, those have a certain expectation of the SQL they want to be able to use. We want to support those. So let me kind of look at a little bit of what we've done so far here, and then I'll walk through some of that in a little more detail. So Hive 11, which came out in May of 2003, that really focused on some base optimizations, and I'll show you some performance numbers later. There was just a lot of places where Hive was doing, frankly, stupid stuff in the way it planned its execution. We fixed a lot of that. As I mentioned, we added the analytics and windowing functions, and this was also the first introduction of ORC file, which stands for Optimized RC file. Another anecdote on that, actually, it was developed by Owen O'Malley, and I had never seen it written out. I just seen it as ORC, so for a long time I actually thought that stood for Owen's RC file, and then one day he corrected me. He's like, no, it's Optimized RC file, not Owen's RC file. So, and that's what it stands for. I'll talk more about that a bit later, but this is basically taking modern technology, the way databases like Microsoft's SQL Server work for their OLAP type operations and importing that into Hive. And actually, that's a place we've collaborated very closely with Microsoft on this work. Okay, so Hive 12, released in October of 2013, so just a few weeks ago. This varchar and date types were added. So I talked about, you want your SQL to be standard, to be what your analysts and your BI tools expect. Standardizing Hive's type model has been a big part of that. Hive initially had a Java-based type model, right? It had string, int, float. These are all things that are very familiar when you're a Java programmer, but string actually doesn't mean much to a SQL person, and it's particularly confusing to other SQL tools. If you try to hook a standard SQL tool up to Hive and you tell it this is a string, the first question it's going to ask is, what's the limit of that? How big can I size that string field? And Hive's going to tell you, I don't know, it's a string, it could be any size, right? So adding types like varchar that are bounded are important for that. We added predicate pushdowns to ORC, so this is the ability to push the predicates down into the file reader itself so that it can, using its internal stats and indexes, it can make choices like, hey, I'm only looking for users that live in the United States, and I see from my index that every user in this block of the file is actually from Europe, so I'm not even going to decompress this block. I'm not going to read it. I'm just going to skip across. that, and again, I'll talk about that more a little bit later. And Hive 12 was the first release that we tested and built directly on Yarn. Now, this is still using MapReduce. It's not using Tez yet. So it's still limited by a lot of those MapReduce limitations. But even just moving to Yarn without changing to MapReduce gave us some performance gain, 20%, something like that. But in general, whatever your application, regardless of Hive, when you move it to Yarn, if it's MapReduce based, we've seen quite an uptick in performance. One example of that is Yahoo, who has moved entirely to Yarn, to Hadoop 2, and has been on it for, well, sorry, not Hadoop 2. They're on Hadoop 0.23, which is the Yarn part of Hadoop 2, but not the HDFS part. They've been in production on that for 9 months. They've actually been able to reduce their compute resources by something like 20% and still process more data without doing any changes to their applications, just because Yarn is so much more efficient than old Hadoop 1. So you get some boost there. So what are we working on now? The work now in the Hive community is to move Hive over to Tez, to start to take advantage of that stuff. To start to do some things like buffer caching, which is now available in HDFS, to build in a cost-based optimizer, and to rework the Hive's internal operators to basically take advantage of the latest research on how you should build OLAP-type engines. And I'll walk through some of that. So let me talk first about a little more in depth of what's actually in Hive 12 feature-wise beyond just performance. So one of the problems that Hive had in the past was for queries that were going to query a lot of data, it was actually very slow to plan the query, even regardless of actually executing it. So say you had a data set where every day, or let's make it even worse, every hour you bring in data from some external system or maybe from your web logs and you put that down. And then you want to do a year-over-year query. So you want to query every hour over the last year. So I can't do 24 times 365 in my head, but there's going to be 5 digits in that, right? You're going to have whatever that is, 15, 20,000 partitions in that query. It would actually take, if you do that in Hive 11, it will take it 2-3 minutes even just to plan that, because it's got to go out and deal with so many different partitions in that data set. That actually is just an inefficiency in the way Hive interacted with its metadata system. So that we resolved that in Hive 12. So now large queries like that can be planned much, much faster. Where it was minutes before, it's now something we can do in a few seconds, even when you're touching a large number of partitions. I talked about the predicate pushdown. Then there's a few other new features, like we can now do order by in parallel. In the past, order bys had to be done in a single reducer at the end of the processing. Now that can be done in parallel, and still you can still get a total order, which is useful if you're doing if you're ordering a large data set. All right, so let me talk a little bit about where we're going with SQL, what we want to do next, and then I have some kind of performance numbers to show actually are we delivering on these promises of speeding things up so much. So in this chart you see in green is all the stuff Hive does. Much of this it's done for a long, long time. In orange you see stuff that was added in Hive 12, so mostly the data type work. And then in blue you see stuff we're actually working on now. So when this says roadmap, but roadmap's a pretty fuzzy term. It can mean, yeah, I'm actually working on this, or it can mean, yeah, someday I think we ought to do that. Everything on this slide that's blue is actually stuff where work is currently happening. There's engineers assigned to it. People are moving on this. So what are the key points here? So adding the car data type, this is just finishing out the data type stuff. Adding subqueries and where and having. This is another point where it's just compliance with what people expect, with what Power SQL users want to have, with what BI tools want to have. And the same in the next point, which is the join syntax. So this is old style join syntax, select star from A comma B where A.user equals B.user. That's not exciting at all, but it's just something you need to have to be compatible with the tool set. There's quite a bit of work going on in security. So Hive is notoriously insecure, and rightly so. The security model is pretty weak. So there's work going on to actually build SQL-style grant revoke type security into Hive. And then one that I'm particularly excited about, because I'm actually working on it, is adding transactions to Hive for insert, update, and delete. Now I want to be really careful when I talk about this, because people see ACID and they immediately think OLTP. We have not gone totally insane. We're not doing OLTP in Hive. That would be insane. But that said, there are still times you want transactions in an OLAP type data store, right? There's still times you want your query to only see the right data set. Let me give you an example of that. Let's say that you want to, you have Flume or Kafka or something like that spewing data into your cluster at a very high rate. Say every 15 seconds it's dropping 100 or 1,000 rows or something, which would be a pretty normal thing to do. Flume or Kafka, either one can do that just fine. HDFS does that just fine. But Hive doesn't do that so well. Because of the way Hive partitions data and the fact that you can't be creating a partition every minute, you can't actually commit that data for 15 minutes or an hour or something like that. You have to build the partition over that time and then you commit it, because that's how Hive works today. But that's stupid, right? Your data is available, it's in your cluster, but your users can't see it for an hour. So you'd like that data to be instantly available. As soon as it hits the disk, your Hive users should be able to be exposed to that data. But if you're going to do that, you need to give them a consistent view. It can't be that I'm running a query and data is coming in since I started the query and I'm getting half of that data but not the other half, or who knows which pieces of it I'm getting and which I'm not. Especially in the MapReduce world where there's things like, or sorry, I shouldn't say MapReduce, in the Hadoop world where there's things like speculative execution, 2 tasks, maybe doing the same work, whichever finishes first is the one that's going to win. If you don't have consistency in your data model, you've got those 2 tasks. What results you see is going to depend on which of those tasks wins. That's not good, right? That's not going to meet the expectations people have for these kinds of systems. So in that case, you do need transactions to manage that. You need to be able to say, okay, I started this query at time X. I only see data that was already committed to the store at that time. But new data can keep pouring in. I just know to ignore it. There are other cases where this is useful. If you're doing slow-changing dimensions, right? You have your traditional star schema with your fact table, dimension tables that are recording who your users are, where your stores are, those kinds of things. If you open a new store in a new city, you want to add that to the stores table. Well, today Hive doesn't do that real well. So we want to support that. And then occasionally you do need to change data. You process a bunch of data and suddenly you realize that you did something a little bit wrong and these 500 rows have a wrong value in it. Rather than be forced to drop all the data processing and go back and rerun it just because Hive doesn't let you update, you'd like to be able to just update those 500 rows, right? Or say a user calls up and says, I want to cancel my service, and you have rules that say once they're canceled, they need, or well, actually a better example is they call up and say, I don't want you to keep records of me anymore. I want out, I'm opting out of your system, and the laws in your area say that once they say that, you have to actually take them out of your system, right? Rather than reprocess that entire table or partition therein, you'd like to just be able to say, okay, delete the records that relate to that user. So those are the kinds of use cases we want to support there. So fast ingest, update or delete of a few records here or there, not tons of little transactions. What we're building won't stand up in the face of tons of little transactions. All right, so let's move to performance numbers. We've talked about we want to make this 100 times faster. Are we really delivering on it? So these are some performance tests we've been running very regularly over the last 9 months. Let me walk you through a little bit of what they are and what they mean. So there's a group called TPC, Transaction Processing Consortium, I think it is. They publish a series of different benchmarks that people can run. And one of them is TPC DS. DS stands for Decision Support. These are queries you would expect to be run in OLAP type situations where people are trying to do, classic big data kinds of things. We picked 2 representative queries from this that we use pretty consistently. We run at least the 27 here on the left. We run every night. We look at the numbers. We run the 82 one pretty regularly too, just to keep track of how we're doing, whether we're making things better or not. So query 27, and by the way, you can look these up. You can go to, I think it's tpc.org, and you can download the query set, and you can look at what query 27 is. But query 27 is just a basic bread and butter OLAP query. It's a star schema with a fact table, 4 dimension tables, a group by and an order by. Very, very simple query. Something that you would expect to return very quickly. We ran this over at a scale 200, which means that the entire data set's about 200 gigs. You can set different scales for this, and we do run it sometimes at the 1 terabyte size, and at, I think we've even run it at the 10 terabyte size. But we tend to use the 200 gigs because basically it allows us to do it on, I believe we run this on 20 machines. We'd need a few more machines if we're going to run it bigger. So the black here, this is Hive 10 using text files. That's cheating a little bit because you wouldn't really want to use text files to store your data. The reason we do this is we find that when people publish numbers about how bad Hive sucks, they always use text. They always kind of pick the worst case for Hive, and then they put Hive in text. They don't partition the data, and then they publish it next to their brand new spanky thing, and they say, look, Hive sucks, we're 100 times faster. And it's like, sure, you are if you do all those things to Hive. So if you actually optimize your data layout and partition it and such in Hive 10, you can about cut this number in half, a little more. You can get it to about 600 seconds. So 600 is really kind of a better baseline there. Hive 11, which, keep in mind, is still on MapReduce 1, still, so not moving to Tez, not even moving to Yarn yet. We pushed that number down to 39 seconds. So that just represents taking, making the planner in Hive a lot better. In the work we're doing now, I called this trunk, but this isn't actually checked into Hive's trunk yet. It's on a branch called the Tez branch. In our nightly runs, we're seeing numbers in the 7-second range. So are we totally satisfied with this? No, we think we can continue to push this down. Are we happy with the distance we've come? Yeah, right? We're making quite a bit of progress against the, our goal of speeding this up 100x. So query 82 is a fact-to-fact join. We put this one in our mix because in these star query joins, like over here on query 27, you can basically load all the dimension tables in memory, and then you only have to scan the one table, right? That's a very standard way. It's called a fragment replicate join or a broadcast join. Very standard way to approach this kind of problem, and we want to be good at that, but we also want to make sure we still work in the case where you can't fit things in memory. So query 82 is a fact-to-fact join. You just absolutely can't fit everything in memory. We still want to be fast. So we're still seeing pretty nice speed ups there from where we were at before. Okay, I got lots more graphs, kind of the same stuff. Well, let me show you this real quickly, actually, because this is still interesting. So this one we ran against Hive 12, and then against the latest stuff. Unfortunately, I don't have numbers for this on Hive 10, but I assume they would look similar to the other queries. But the basic notion here is, even over Hive 12, we're seeing quite a bit of speed up, and this is the Tez work, right? That's really doing that. So I'm going to, in the interest of time here, skip ahead a bit. So what is this stuff we're doing that's making this speed up? Obviously, I said the Tez stuff. There is the work on the ORC file that I talked about a little bit. The other big thing is this vectorized work and putting a cost-based optimizer in here. Now, this work isn't actually in those numbers you saw. Our cost-based optimizer is still under development. But the realization of that we came to is, in the past, Hive could work with a rule-based optimizer because it was simple enough that the rules were always good enough. But as you get more complex, as you take on these big queries with many, many way joins, you need a cost-based optimizer. Only that can tell you how should I order this join. There's no rule that can tell you I should order it this way or that way. So we've actually partnered with a project called Optic that you can think of as an optimizer generator, sort of in the same way that Antler or Yak are parser generators. And we're starting to use that inside Hive to build a true cost-based optimizer for Hive. So let me pick a couple of these and talk a little more in depth about what they do. So I kind of touched on ORC, that it's a modern format. So what's that mean? What that means is it's columnar. People have known for at least 10, maybe 15 years now that whenever you're doing these kinds of OLAP queries, you want a columnar store, right? That's almost always a win for these query types. You want your storage to understand your data model. Up to date, all the standard storage options in Hive are C file, sequence file, text. None of these actually understand Hive's type model. By the time it gets to the storage level, it's just a series of bytes. That means the storage layer can't think about how to optimally compress this, because depending on your data type, there's actually different compression options that work better. For example, if you know something's an integer, you can variable length encode it in a very nice way, right? In a way that you can't necessarily with strings. If you know something's a string, you can use dictionary encoding on it. These are the kinds of things that ORC does because it understands the data model. It also keeps built-in indexes about this data so that it can tell in a given stripe, what it calls stripes, which the thing is, eventually you run out of words. You'd like to call this a block, but a block's already something on disk, and a block's already something in HDFS, so you end up calling them a stripe. So in each ORC stripe, it keeps index information about how many records are in here, what's the max value I see, what's the min value. It's got that dictionary, so it knows what values are in there. And as I alluded to earlier, that gives you a lot of advantages when you want to do predicate pushdown, right? I'm scanning through the data. I can use those indexes to figure out whether I should look in this block at all. It's also useful for query planning because you can use it for statistics, right? When the query planner wants to decide how should I order these joins, it can look at this information and figure out, okay, I have about this many rows, I have this many distinct values, that means I estimate the join will come out this way. All that's very valuable. All right, so on top of this encoding I talked about, ORC file also allows you to do compression of the data after it's been encoded. So you can use zlib, you can use snappy or LZO. By default, it uses zlib. So the results of that look like this. It compresses down very nicely versus original text or even RC file. You get some very nice compression ratios, obviously depending somewhat on your data. ORC has been a collaboration between us, Microsoft, and Facebook. And Facebook's actually been interested in it primarily for its compression, not for its other performance capabilities. Not that they won't take advantage of that, but they're very excited about the compression because they have something like 50 petabytes under storage, and at some point, even they run out of money to buy more disks, right? So this kind of stuff's very exciting to them. All right, in my remaining time, let me kind of hit on two other brief things we're doing here. I referenced the vectorized query execution. The observation here is that database engines used to be built, they were originally built to process one record at a time. You'd set up a pipeline of operators, and you'd pull one record at a time through. It's an easy way to write it. It's what all the textbooks say. It's the way Hive worked, or works today. But it's been known for 10 years or so that what you really want to do is you want to process blocks of records at a time. You want to choose that block such that it fits in your L1 cache so that you don't have cache misses when you're processing that block. And you want to write your code so that there's no function calls or branches in your inner loop so that you're never stalling your pipeline. The whole goal here is you don't stall your pipeline. A cache miss costs you about 100 clock ticks, and a pipeline stall costs you 10 to 15, depending on the processor. So that's very expensive. So we're going through and reworking Hive's operators to take advantage of that. This is work that we're doing in conjunction with a team from Microsoft that did this same kind of thing in SQL Server PDW. So they saw very significant gains. Our early work, we've seen something like 40x speedups in processing of a single task as a result of this. You can be processing up to like 100 million rows a second on even a pretty weak machine like a laptop doing these kinds of things. And then finally, buffer caching, right? It's great to be fast off disk. It's great to be parallel, but sometimes it's, no matter how fast your disk is, no matter how parallel it is, memory is always faster. If you have a hot data set, you'd like to be able to keep that in memory and keep processing that. The latest release of HDFS actually enables that. It enables users to pin certain files into memory, or actually I think it allows you to pin blocks. Hive can take advantage of this to pin like dimension tables or hot partitions of a fact table into memory. So that's also work that we're doing that you saw in those performance numbers, so that for pieces that really matter, we don't even have to go to the disk. All right, and with that, I will go to questions.
Tomados para que saquen, si no quieren.
Any questions? Oh, sorry, up there, I couldn't see you.
Hey, hi. You talk about CVO for Hive and about the gathering statistics for the CVO.
Yes.
That's an expensive thing, gathering statistics. You know how, or you have an idea how you're going to make about it?
Sure. So yeah, that's a fair question. It can be, statistics gathering can be expensive. There's a couple levels, right? So today, Hive can gather row number and cardinality of individual columns, and that you can actually do pretty inexpensively. And you can make some estimates. They're not perfect, but you can make estimates off that. That's actually what it has so far today. What is expensive is building histograms, and that we haven't solved yet. So there was actually one, the work to gather the cardinality and row numbers was done a while ago by some people at Cloudera. They did that really well. They took a swing at the histogram stuff and didn't quite get it right. So there's, and I don't mean that badly, they would agree with me. They didn't feel like it performed well, so they didn't use it. So there's still work, I think, to figure out how to do that quickly. But I mean, the thing is, you can gather minimal statistics on load at low cost and then allow users to say, okay, I want to go back and pay the cost to gather more precise statistics and to speed up my queries, so that you can let that part be user determined whether they want to pay that cost or not, whether it's worth it to them. Because if you're going to read and write the data once, you probably don't want to pay the cost. But if this is data you're going to read over and over and over, it's worth it to pay the cost, right, to gather those statistics. Other questions? Yeah.
What about compatibility? I mean, you have a cluster with Hadoop 1.0, and you want to migrate to Hadoop 2.0 because really it looks amazing, and congratulations about the work. What effort it will require?
Sure. Very good question. So there's no need to move your data or anything to migrate from Hadoop 1 to Hadoop 2. Unfortunately, you do have to turn your cluster off to do the migration. There's no rolling upgrade, but you don't have to move anything. You can turn it off, switch the software, turn it back on as Hadoop 2, and it works. We test that repeatedly. We do it with our customers, so we know that's something that works. I should also touch on compatibility, because I talked a lot about the ORC file, how that's enabling some of the stuff we want to do. You're not required to switch to this file format to get all these benefits. You are to get some of them, but not all. And even if you decide to switch, you don't have to go back and restate your data, right? If you have terabytes of data in some file format, there's no need to restate that. Hive and Pig and MapReduce can handle the fact that some data sets are in one format, and some partitions, older parts of your data are in an old format and new are in new, right? So you can just say, okay, as of today, I switched to using ORC file, but previous partitions are still in sequential or RC or text or whatever you used. And as the query, when the query spans across those, Hive will handle planning that, going, okay, I know mappers or tasks that read this need to use the old format, tasks that need to read the new, use the new format, and that just works.
Okay, is it possible with Yarn to integrate processing with Storm, just to put an example, with MapReduce or something like this at the same time? I mean, I have a lot of data in batch, and then I have data coming in streaming, and I want to do something to analyze with Storm and with MapReduce. Is it possible, or is it for the future? Or?
This is possible. And it's possible today, right? That is exactly what Yarn is designed to enable, is that your cluster shares heterogeneous processing loads in a way that keeps them from battling each other, right?
Okay, thank you very much. Thank you very much, Alan.